Thank you very much for the invitation and for organizing such a nice seminar in this kind of, let's say, crazy times and, yeah, keeping some kind of normality here. I realized that my background actually fits fairly well. Here we have one world. And so thanks everyone for joining, and I hope all families are safe and stay safe in the next couple of months. So I will talk about inverse optimal transport. So I was kind of happy when I saw that Gabriel is going to give the first talk, because I'm like, he's going to set the scene. And so, yeah, thank you very much, Gabriel, for this excellent talk. Kind of saved me a lot of work. However, this kind of talk is now, as Martin already said, going to focus on the inverse aspect of the problem. And this is a problem that I started to work with Andrew Stewart while he was still back at Warwick University. He's now at Caltech. And today I'm going to present, upon request, what the first outcomes of this project are. So the question that I'm going to address is the following. So it's a rather general problem. So if we have some kind of input criteria, and we know that I have a problem where the solution, the output, depends on some kind of cost, on an optimal cost criterion, the question at hand is what if I know the transformation from the input to the output, but I have no idea or only partial ideas about the underlying cost criteria. And we have already seen that there are several applications where you can kind of think about that. The first one is optimal transport, where, okay, it goes back to our very general problem that we have two probability densities and we want to find the optimal transportation map according to a cost criteria. So we could, for example, here know or observe the transportation map, but we don't know the cost criteria. This has applications in data science, but one could also go a bit back and you can just have the question of a linear assignment problem, which in general also fits into the optimal transportation problem, but also applications, as I said, in matching or assignment problems in economics fall into this criteria. So the general outline of the talk is then I will give you a couple of problems where you will run into what I call now inverse optimal transportation problems. So the first one is actually some work which was done by Gabriel Perret and co-workers. The second one also goes back to French, or the French optimal transportation community. It's the well-known marriage market problem. And then the third application is a problem that I have worked on. It's on international migration flows. And so at the beginning, I will kind of set the scene and give you an idea what kind of problems have been looked at in this context, what are the applications, before turning to actually what is the forward problem. Since I'm going to talk about inverse optimal transport, I have to define what is the forward problem, and then looking in the last part at the corresponding inverse problem. And we're going to solve this inverse problem using the Bayesian framework, and then I will present you some first results. Okay, so we've already had a very beautiful introduction to optimal transport, but I will just kind of reiterate also to set my notation here. So in my setting, I will always consider two discrete probability vectors, P and Q, and some given cost matrix. And I want to find, so to say, the optimal transportation plan, mapping P to Q. So my set of feasible plans is not U here, it's called S, at minimal cost. We have seen that this problem, it goes back to Wolfram, who actually looked at the pile of sand and he wanted to find the most cost-effective way to move one pile of sand to another if they have the same volume. And as Gabriel already pointed out, this problem, not all of these problems they have, there is a solution, and the first major step was the Contourer relaxation, which was in the 1940s, where the mass could be split, and so you can find a solution to this problem. And in general, if we have a discrete optimal transportation problem, so as in the last talk, then this is, if you just go back to your optimization or basic first class on optimization with constraints, then we know that such a problem has at least one solution, and it lies so your marginal constraints define so to say, your feasibility set, and the solution has to lie on the boundary of this feasibility set. So this is just a very general setup that we have for discrete optimal transport. And if you go now to applications, then often you're interested in the question, for example, it's called ground metric learning, is, okay, let's assume I have two kind of data sets, and I want to have an observation how these data sets evolve. In your last talk, what we saw is, for example, this kind of motion between, I think it was, yeah, if I would remember, but kind of the barycentric interpolation between two histograms. And if I have certain instances of it, then I would like to find, so to say, the underlying cost criteria. And this is what those Gabriel Perret and co-workers were working on. So what is well known is that if I have, we have already heard that before, if I have some kind of, my cost matrix defines certain conditions, then the solution to my optimal transport problem defines a metric. And in this metric, now I can calculate the, so to say, I can interpolate or find the geodesic which connects my two probability measures, so the P and the Q. This is the well-known Lacan interpolation. So these are just straight lines in my Wasserstein space. And what you want to look at in ground metric learning is, okay, given two data sets, and I have, so to say, observations of those data sets at different times. So this is this P of TI. And I know that my cost defines, so to say, an interpolation between my initial and my final density with respect to some matrix CW. So this is now my cost matrix, and this cost matrix depends on weights, which are, since this problem is defined on graphs. What they were interested in was, okay, how can I find the optimal weights such that I minimize a given loss function. So this is what we see, what they considered in this kind of context of ground metric learning. So here the idea was, okay, I would like to identify weights of an underlying graph, which, so to say, define my cost that is unknown, given notions or instances, snapshots of my probability density at certain times. The second problem that was more looked at in the setting of economics is it's what's called learning how to match with optimal transport. So these are very recent papers in machine learning community. And here the question was rather similar. So we have two given probability vectors P and Q hat, and you observe the matching between the two. And you want to estimate now the cost by minimizing the negative log likelihood. So this was the objective that these colleagues were looking at. And they were interested in several applications. So for example, they had a look at the New York Taxi Data Challenge. So this is a data challenge on Kaggle, where you can get the taxi records of taxi drivers and passengers and how they were matched over a period of 1 year. And they use this data set to find, so to say, the underlying cost criteria and estimate, so given a certain data set for a certain time period, can I predict the dynamics for other time periods, and they compared the results. In the second application that I will show you in a minute, it's the so-called marriage market problem, where this was studied by economists. So there is Alfred Gallichon, who worked a lot in this field, where you also want to sort of say identify, in this case, since it's economics, so we're not minimizing costs, we are maximizing now. Okay, just put the minus in front and we're fine. So you want to find out the maximum surplus. I will explain to you in a minute what that means, to find the optimal matches between two sets. And in the marriage market problem, you always look at, so to say, you consider male and female, and you want to match them according in such a way that all of them have the best, so to say, outcome or the best matching according to some surplus criteria. What are the challenges that you have here in general? The problem is ill-posed. So one has to think about the suitable regularization. In the previous example, you already probably spotted a term which was called f of w, so you have to add some regularization term. Furthermore, if you have large problems, then you have a high computational complexity, and we've seen in the last talk that, okay, if I have large data sets, I can still solve the linear programming problem, but that's quite costly. You might want to have a look at the regularized OT problem. And then you also might want to look at suitable parameterizations of your cost. Just to conclude, the example that is also quite nice here is this marriage market problem. So again, we have now vectors Q and P, and you can think of them, as I said, as male and female. And in this setting, what you have is they are split in groups. So you have different kind of age ranges, education, income. And if I, so to say, match male and female, then this creates some social surplus. And each of the individuals want to maximize their surplus. And what they were looking at was actually a formulation like this. So they said, really, you want to find an optimal method matching over our feasible set, which maximizes now our cost or social surplus. And also here you see again a term, this H is the entropy, so they already considered the regularized problem. And they had a look at the inverse problem, and I will show you the results in a minute. The problem here, what they were actually studying, goes back to, as I said, this marriage market problem. It has been studied by a lot of economists, but looking at it in the optimal transportation setting, it was Alfred Galicon mostly working on it. And so what they did is that they looked at, and also Chu and So, and they looked at the data sets from 1970 and 1980. So they had the US Census data, as well as the marriage records from the years 71 and 72 and 81 and 82. And they wanted to have a look, how did the marriage behavior in this period change? Because in this period, there was a lot of changes due to developments. I mean, there were contraception coming up, but also there was Roe versus Wade, which was in 73, and abortion was legalized. And the question was, did this, so to say, affect the marriage behavior? And what they found out is actually, so they wanted to estimate this social surplus criteria, or cost criteria, so this matrix C. And the outcome was that indeed you could see significant shift in the values of the cost criteria. And it's also kind of nice if I took a plot from one of their papers, is that they had a look at, after estimating the costs, at the number of available males and females after the estimates, and you can see that, so to say, there was a certain number of people according to the cost criteria were matched with the data, and others were not, and the number of available males and females after in 81, 82 was across all age ranges, so to say, higher. So, and they found that there was indeed a significant difference, so to say, in the cost criteria that they could spot looking at different methods. The last application that I want to tell you about is now the one that I will focus on. So we started to look at the problem, and this was initialized by a discussion from myself with Guy Abel. He is a demographer and working back then in Vienna, and he's producing these beautiful charts that you can see here. And in international migration flows, what you do is you report, or you want to estimate the numbers of people moving from one country to another. And these migration flows, they're collected by international agencies. So for the European Union, it's the Eurostat. Worldwide, it's the United Nations. And it's kind of surprising if you look at data that there are actually no real international standards. So depending on where you come or which country you are coming from, so even in developed countries within the European Union, the data is not what we call harmonized. If you come from a developing countries, there's even less data available. And there are two types of data, and I will only focus on the second set. This is called flow data. But the first data is called stock, and this is the data that is collected in census, like when they count the number of individuals in a country, and what you have, this data is usually available every 10 years. And also for less developed countries, it's much more reliable. So we count the number of individuals living at a certain point in a country with respect to their birthplace. The flow data is usually reported annually, and it just tells how many people moved from one country to another. And if you want to have a look at the data now, so this is what I will call the origin to destination matrix. And this is taken from a paper from 2010. So it's more or less recent. And it's already called harmonized data or the flow statistics. So this is now telling us how many people moved from the Czech Republic, for example, to Germany in a year. And the RNDS, it stands for reporting and sending countries. And so the number, receiving and sending countries. So if you now look at the numbers, then you might say, okay, some of them are close. So Denmark, for example, to Germany, we have 2,600. Both of them say roughly the same. So Denmark said, okay, Germany said we received 2,600. Denmark said the same, 2,612. But one of the biggest discrepancy is Poland to Germany. So Germany reported that 136,000 people moved from from Poland to Germany, while Poland said 14,000 left. So you can see that there is quite a significant difference. The difference, as I said, there are no standards. Second, also, it's not mandatory that you register in every country where you move to, and it's also not mandatory to deregister. In this case, usually the receiving numbers are considered the more accurate. But as you say, this is the European Union. This is harmonized, but still you can interpret this now as a transportation map, but it's a very noisy one. So to say, you have a lot of data missing, and the numbers that are reported, as you say, they can vary significantly. Okay, so just before starting, I will, so to say, set up some notation that I will use in the following. So just to kind of set the scene, as I said, I'm talking about probability vectors, so by P, and I usually always have vectors and matrices which are normalized. S, P, Q, as we've seen before, this is my admissible set, which satisfies the marginal constraints. And later on, when I do the identification, it's often much easier to kind of, when I'm searching for candidates, it's easier to search in spaces that are not, so to say, if my vectors are not normalized. So I define mappings, we denote them by MN. Just remember these, make sure that, so to say, the variables that I will then later on work on are indeed normalized and fall into this class. It's just a bit of a technicality. Okay, so as I said, I don't have to do much now because Gabriel already set the scene so beautifully. But still, I have my two probability vectors, I have my costs, and we have seen the optimal transportation problem already. So I want to find my transportation map according to the cost criteria. And if you look at large scale problems, as we have learned before, it's probably advisable to have a look at, so to say, the regularized OT problem. So instead of considering just the minimum with respect to C and T, we also add our discrete entropy here. And the first advantage that one would also say is that, and now I have a unique minimizer because in the other problem, I have at least one solution which lies, as I said, on the boundary of my feasibility set, but now my problem is strictly convex, so I have a unique minimizer. And we have seen this already before, that the nice thing about adding this entropy is actually that we can now rewrite the system in a very nice way, or our problem. We see that this regularized optimal transportation plan is actually the minimizer of the corresponding formulation if we use the Kullback-Leibler divergence and the Gibbs kernel, before, that we can write it in a very smart way. So this is just recalling that you can use Synchron's algorithm. It's much faster. It allows you to compute these transportation maps in just using my matrix vector multiplications. And so this is really very efficient. However, there are a couple of things, and One nice thing that I would like to point out, I just read a paper very recently. It's from Martin Idle from the TU Munich, who kind of said that this synchron algorithm, it has been around for such a long time, and that important results that kind of are rediscovered over and over again, and gave a really nice overview when so synchron, he was the first one, and then how it continued and how this algorithm was kind of yeah, developed or discovered again within the communities. So, but synchron in the last years now for optimal transport, it's one of the tools that you want to use if you want to be fast. However, one of the things that we have is we introduced this into our regularization term. And originally, what we had is that the transportation matrix is sparse. So Gabriel showed this very beautiful plots where we could see that we have really a straight line, and as we increase epsilon, it starts to get blurry. So if you think of pedestrians or international migration flows, then the question is, okay, do you allow for this kind of regularization already in the forward problem or not? But this is also a question of modeling. In terms of computational efficiency, it's certainly one way that one can go. And the nice thing is also there are good libraries. I missed the reference here, but if you want some Python libraries, I think just go to Gabriel's webpage or look at the book. They point you in the right direction, and there you can find very efficient algorithms to solve this. Okay, so now let's talk about how we can use the optimal transportation problem in the context of migration flows. So, as I said, this was the main application that we started to work on. We learned about the others kind of along the way. And the question here was, okay, we have now our transportation map, so the origin to destination map. And we were saying, okay, let's say that individuals move and they want to minimize certain costs. So they move from one country to another, and moving from one country to the next one, it always comes with costs. So we say that this origin destination matrix can be interpreted as a very noisy estimate of a transportation map. And the cost is unknown. And in the context of migration flows, we were assuming, okay, let's connect this cost to an underlying graph structure. And we kept it simple for the time being. So on the right, you can see a network structure, which is defined by the European Union or the countries within. It's not the European, the Switzerland either, sorry, in Europe. But it's a small network. It's 9 countries, and they're connected by so they have a connection. So the weights between them, they have a connection if they share a border. So we did make things easier. We said, okay, you can only travel from one country to another if they share a common border. So we are not flying here. It's just overland travel. And so this is now our graph structure and the underlying graph structure. And the cost of moving corresponds to the weights, so to say, along the graph. And we also assume that everybody moves. So staying is not possible. So we penalize, so to say, staying in the own country. So if we now want to calculate graph-based cost, what you do is you define, so to say, the underlying graph. So we have n countries, these are our vertices, and we have an adjacency matrix. As I said, we only connect countries which share a common border. We have only overland travel, and the weights are, as I said, the cost of moving from one country to the neighboring country. And it doesn't have to be, it might be that the costs are different. So moving from, I don't know, Austria to Switzerland, the cost is different than moving from Switzerland to Austria. But so this was the general setting. And now if I want to compute, so if I know all the individual costs along my edges, then you can compute the cost. And we said, okay, this is the shortest path. So I'm taking always the shortest path along my edges to figure out what is the minimal cost. And if you look at, I think it's maybe optimal control nodes, then you will find that you can calculate this optimal cost using Dijkstra's algorithm. So this is, so to say, then defining, if I have now my non-zero entries of my adjacency matrix. So this adjacency matrix just tells me if countries are connected. The m entries, they define a vector, and the variable, or what I call here curly e, is now just the Dijkstra, or the application of Dijkstra's algorithm, taking the non-zero entries, which are my connected countries, and mapping them to the cost criteria. So this is how we relate it, so to say, optimal transport to a migration flow international, or just some graph-based structure which tells me how individuals can move at certain costs from one node to another. So now I will talk about the inverse problem. So for the inverse problem, what we are now interested in is, okay, as I said, we have this origin to destination map. So I have an observation, and I want to determine my marginals P and Q, as well as the cost, from a possibly noisy observation or solution of the OT problem or the regularized OT problem. So there I have the choice if I set epsilon equal to 0 or if not. And the forward problem in our setting, it defines a map. So in the classical way, I will work here, this F, we have seen it before, this is the solution. This is just the solution from my marginals and the cost to the transportation. It defines this mapping. And the MN, you remember, this is just to make sure that I'm in the probability, so that my the vectors M are indeed probability vectors. So this is just a mapping to make sure that everything fits into the right spaces. So now we want to find the underlying cost criteria and P and Q, given some noisy observations. And we will use the Bayesian framework. And what you do in the Bayesian framework is that you want to estimate the posterior distribution of coefficients. In our case, these are the entries of the matrix based on prior beliefs that I have. So I have to give some or state some assumptions. We already said it's an inverse problem, so it's ill post. I have to make some assumptions here. And we want to quantify the uncertainty in these estimates. We will sample from this posterior distribution to kind of see how uncertain is our estimate. And I will show you how you can do this for a very general class of optimal transportation problems. So first of all, the question is this an over and undetermined problem? Is ill post? No. So if we now look at our problem in the very general setting, so I have my matrix C, and we remember that I don't allow anybody to stay in the country. So I have my Z bar around the diagonal, and then I can do a couple of counting exercises. And we did, so to say, generate certain toy problems to see if the whole idea works in general. So we made two assumptions about the cost matrix at the beginning, which have nothing to do with the graph-based problem, where we just said, okay, I know my cost matrix has a tuplage structure, which in the context of migration flows makes not much sense, but this was the simplest setting. So let's assume C is toplets, then you can count the number of degrees of freedom in your matrix, you count the number of equations you have to find by the optimal transportation problem, and then you even see that the inverse problem is overdetermined for n, which is the number of countries, or so to say dimension larger than 3. If you have a non-symmetric cost, where you now allow that the weights or the cost of moving from one spot to another, they are not, so to say, the same, then the problem is actually underdetermined. So if n is larger than 2, you have to do the same calculation that we did before. And if you have a graph-based problem, then it depends on the number of edges. So m is the degrees of freedom. This connects to how relates to the number of edges that you have between your nodes. And then you can see, can give a certain criteria if you have an over and underdetermined problem. Okay, so in the Bayesian framework, what you assume is, first of all, that you say, okay, my observations are corrupted by noise. So I make some assumptions about my noise. And here we say we have an additive noise. We denote it by eta. It has mean 0, and the variance is sigma squared. And then you want to, so to say, minimize your model data misfit function. So, okay, this is my model data misfit function. So here is my observation minus, and this is this mapping from my vectors U, V, and W to the transportation map. Okay, so U and V, these are the two probabilities, so to say, they correspond to the probability densities. W here corresponds to my cost. So then, given this kind of sample, I can calculate this transportation map. I look how much do they differ. What is this is just a misfit function. So now in the Bayesian framework, you use Bayes formula, which tells us that the posterior, so the posterior distribution to have for u, v, and w, given an observation t, is equal to my likelihood and the prior information that I put on the variables that I want to identify. So first of all, we can have a look, you can compute, since I assume that I have Gaussian noise here, the probability of observing t, given some realizations of u, v, and w, is given by this exponential. Then I add my prior information about the variables u, v, and w. And in our case, and one can argue about this, we also had a look and we were thinking of, at the beginning, normally distributed or Gaussians. But in this setting, we assumed that u, v, and w are uniformly distributed within 0, 1. And then you can write down the posterior distribution. The c is a scaling constant. So this was also in the previous and Bayes theorem. You can write down your posterior distribution. And what you do then in the Bayesian framework is you can sample from this posterior distribution. So now what you have to do is, okay, you want to sample, and this is a different type of methods available. And what we are going to use, and what Andrew Stewart is working very heavily on, are Markov, well, a lot of Markov chain Monte Carlo methods. So where we draw samples, and by drawing those samples, we do this in a systematic way. I will show this to you in a minute. And this then will compare the outcome of the transportation map with the actual observation, and we either accept or reject. And we do this many, many times, and in the end, we will hope that this converges towards the, so to say, posterior distribution of the variables we want to identify. This is not the only way you could do that. You could also just maximize the posterior over your set, and just to obtain a point estimate. It depends on what you're in the end actually interested in. Okay, so how do you do that? That looks a bit ugly here. It's probably my fullest slide. You can do a random walk metropolis within Gibbs. So just to give you an idea of what this is doing. So if you look at this, you're just like, what's going on here? In principle, you have now your parameters you want to identify, u, v, and w. So, and then you have your initial value, and you draw, so to say, a new sample. So this is you generate some new proposals, which I call X. Then if my new sample satisfies my constraint, you remember I have to be in the set 0, 1. So then I will calculate the new transportation map, and I will have a look with, I compare this new transportation map to the one that I had before. And this acceptance rate on the bottom tells us if I'm doing better, I will accept this value. And if not, I will reject it. Then you do the same for the V, and you do the same for the W. So this within Gibbs means that you split it into all the 3 steps. I mean, you could do it all together. What we did here is within Gibbs, so we had a look at them different, each one of them. And you have certain parameters that you can choose. So the space, so to say, where you search for new candidates, these are, this is so to say hidden in this deltas. So how much do you explore the space? And we will have a look now in the computational examples, how much does this influence actually our outcome. So we are, so to say, now, as I said, we sample, we draw new samples, and we generate those, and we decide, okay, do they give us a better approximation or not? If yes, we accept them, otherwise we reject them. We do this many, many times. You will see that I've done this 100,000 times, which means that every time you have to solve an optimal transportation problem, if this is large, this is getting computationally costly, and this is the reason why you probably want to look into entropy in the regularized problem, because, well, as I said, you have to do it many times. Okay, so this is the first third problem that I want to show you, and just to give you an idea. So first, this is Toeplitz cost, and if we go back, or if you remember, in case of Toeplitz cost, the problem is overdetermined. And what we did there is we took our truth, we generated the transportation map, we added 4% of noise. We had 5, so to say, countries, and then we wanted to estimate the components of U, V, and F. F is now just in this case, because it's a Toeplitz matrix, then you can write it as a vector. This is just the entrance of the triplets matrix. And what you see here is that we varied the sampling variance. So we changed the sampling variance. So red and blue corresponds to how much do I explore my space. And on the bottom, you see how often did I actually, so to say, sample from the posterior. So how often did I draw samples and decide, okay, do I take it or do I reject it? And you see that it's converging fairly quickly, first of all. The second thing, it converges to the same thing. And this is something that makes us, so to say, happy, especially Andrew. If he sees, okay, I'm going to vary the variance, I still get the same results. And if you plot then, so to say, the posterior distribution, so the straight line, the black line here, that's always the truth with whom I, so to say, generated my transportation map. And you can see that you get most of them fairly nicely. Some you don't, but it works fairly consistently here. Okay, so but one thing that was kind of something that was interesting for us, or where we kind of were wondering, is in this first example, what I did is, since n was equal to 4, I could just use a straightforward linear program or a simplex algorithm to solve the OT problem. I mean, this is not computationally costly, but we were interested in, okay, how does this behavior change if I now, instead of using the exact solver, I rather use synchrony. And here you see 3 lines or 3 colors, red, blue, and gold. And the red is just the exact linear program, while blue and gold correspond to synchrony. And there you choose, now you have to choose your regularization parameter. And gold, you see that we chose a rather large value. It's 10% already. And then, even if we are in case of tuplets, which is overdetermined, the results, they get worse. So you see a significant difference, which is not, so to say, surprising. If I, so to say, regularize my forward solver already, I'm introducing additional noise to the problem. But it's very little is known how actually the convergence rates of the transportation map. So this is an open problem if one wants to look at it in the, so to say, discrete setting, but you see significant differences here. If you just look at the posterior distribution, so again, the plots, you know, this is where we have our, this is the exact solution. With synchrony, if the, what we observed was if the regularization parameter has roughly the same, is of the same size as the noise level. So in both cases, we had 0.04, we got really good, still good estimates. While if you choose it too large, so this was for the 10%, you see that you don't pick it up very nicely anymore. If I have non-symmetric costs, the problem is underdetermined. I already told you for n larger than 2. So here we chose n equal to 5. Again, we generated our data ourselves in this case and added 4% of noise. We still were able to pick up some values fairly nicely. But if you look at this, we start with some uniform distribution. And since this has to be scaled, this tells us actually that there is not enough information anymore in our data to identify these parameters. So we see what is kind of to be expected, that as we increase, so to say, or if we consider non-symmetric costs or higher dimensional problems, we can't expect that we identify all the parameters. You can also play with graph-based problems. So just to show you, in this case, this is a final, so to say, toy problem where we had a graph with 5 vertices and we connected them with 12 edges. In this case, it's overdetermined, and you can play again with the different sampling sizes. And we pick up also for this graph-based problem, if we generate the data ourselves, things really nicely. One can say, okay, this is all nice. You did it, you generated your data yourself, but what about real data? And so the last thing that I want to show you before I'm finishing here is, I already showed you this picture of this European network of 9 countries, and you can draw the edges, and then you have 30 edges, and you can take the migration flow statistics that I showed you. They define one transportation map. And I used only the receiving countries. So I didn't take both sets, I just take one of these sets. And we assumed that the noise level is 4%. And we want to estimate the parameters using the exact as well as the synchrony solver. And here I used as a regularization parameter, again, this 0.04 as guided, so to say, by these previous examples, we saw that we received got very good results for this case. If you do this, then I don't know the truth anymore. But here you can see the posterior distribution for example, this is the cost of moving from the position, people in Germany and France, as well as the cost of moving from Germany to France. And we got very similar results for the linear program as well for the synchron, and it converged. So I didn't show you the running averages, but you would see that they converge. However, if you want to do this example, this will take you probably, it took me a week until we had that done. You have to do it 500,000 times, and it's a much bigger problem. So some of the coefficients we could pick up very nicely, others, again, not that well, but we were fairly happy with this first consistent results. Okay, just to conclude, what I showed you is how you could formulate these inverse optimal transport problems using the Bayesian framework, and also how you can connect graph-based structures which define your cost to the optimal transportation problem. This defines, as I said, some new way how you can study migration flows, and it gives you a way or a tool how you can quantify and computationally compute estimates for cost criteria. What we are currently looking at is, okay, I just talked about the discrete problem. Would definitely be interesting to have a look at continuous formulation. The second thing I haven't touched yet are data assimilation techniques. So this is kind of a subset or part of inverse problems where we do have actually we have consecutive updates of these transportation maps. So as I said, the flow data is reported annually. So one could take this, first of all, to predict, and second of all, to kind of improve the estimates. And also have a look at different priors and also more complicated models. I mean, it's also here not clear that if you have, for example, here you have certain assumptions on your priors, which allow you to calculate the posterior. This is not always possible. And then one has to look at approximation techniques or approximate Bayesian computations. So there are a lot of directions one could have a look at. And with this, I would like to conclude. These are the references if you're interested in. Also the applications. So this is the work that I did with Andrew. Then I have the works by on ground metric learning, and if you're interested in marriage market problems. And in the end, thank you very much for your attention, and yeah, take care and stay safe.